Example 8. A fisherman in a boat is 6 kilometers straight offshore and wishes to go to a point on the shore that is 10 kilometers from his present location. The fisherman can walk at a speed of 8 kilometers per hour and row his fishing boat at a speed of 4 kilometers per hour. To what point on the shore, relative to his present position, should the fisherman row in order to maximize his travel time? So this is actually very similar to the last question, except this time we're dealing with time instead of cost. But there's a rate at which he can row, and there's a rate at which he can walk. Okay, so we need to figure out sort of that sweet spot of where he should land on the shore so that he can take advantage of the fact that he can walk faster than he can row. So just like before, a diagram set up very similarly. Okay, X this time is actually what we're looking for, because we're looking for how far along the shore should he land. Okay, so X kilometers along the shore would be that blue point right there. And since we're dealing with time and they give us speed and distance, or we use speed and distance, then we are going to have to relate time to distance and speed. Okay, and if you've seen these triangles before, you can use that to remember it. So remember that time is equal to distance divided by speed. Okay. So we need to do some declaration statements here. So we're going to let T represent the total trip time. So in other words, the amount of time on the boat plus the amount of time walking. And we're going to let R represent the distance traveled by boat. So R is going to be that hypotenuse right there. So our big T, our time, is going to be time on boat plus time on land. Or time spent walking. So to find the time on the boat, we're going to do the distance on the boat divided by the speed of the boat. So distance on the boat would be R. Speed of the boat is 4 kilometers per hour. Okay. And similarly for time on land, we're going to do the distance on land, which would be this right here, so that 10 minus x, and divided by the speed on land, which is 8. And just like the last question, we can rewrite R in terms of x, right? Because it's 6 kilometers offshore. That's one side of the triangle. We know that x is the other side of the triangle, and we're finding R. So R would equal the square root of x squared plus 6 squared. So we can rewrite our R in terms of x. We can replace it with that x squared plus 36 over 4. Okay. So now we have time all in terms of one variable. So now we're going to be able to take that derivative in order to minimize the time. Okay, so pause the video, give the derivative a try. Okay, so we took the derivative of that square root function, brought that half down in front, left the inside alone because it's the chain rule, decreased the power by 1, and then following the chain rule, we multiplied by the derivative of the inside to multiply by that 2x. Okay, and that divided by 4, that 1/4 bit, it just stays there because it's a coefficient and we leave coefficients alone. Okay, and then here, the derivative of 10 is 0, derivative of minus x would be -1, so we're left with -1 over 8. We can simplify this a little bit, right? We have the 2 and we have the half. Those will cancel each other out. Okay, and then we can, of course, bring this negative power down to the bottom. Okay, so we would be left with x over 4 times the square root of x squared plus 36 minus 1/8. And now, of course, since we're minimizing, we are going to set our t prime equal to 0 to find those horizontal tangents. I'm going to move that 1/8 over to the other side. And then I'm going to multiply both sides by this 4 root x and by the 8. So multiplying by the 4 root x would leave me with a 4 root x squared plus 36 on the top, and then multiplying both sides with 8 on the other side would leave me with an 8x. And now we do have a factor of 4 on both sides, so we can divide out that factor of 4. And we're left with the square root of x squared plus 36 equaling 2x. And at that point, just like before now, we have the square root equal to one term. We can square both sides. So if we square both sides, we get x squared plus 36 equals 4x squared. And then we isolate the x. So move all those x's over to the other side. Would leave us with 3x squared. Divide both sides by 3. We get x squared equals 12. And then our last step is to square root that 12. And once again, we are going to ignore the negative root, since x is a distance and x has to be greater than or equal to 0. Okay. So we now know what x is, and if we remember back up on the top here, the actual question they're asking us, to what point on the shore relative to his current position should the fisherman row in order to minimize his travel time? So we actually found x, which is what we were looking for, so we're done the question. We don't need to find anything else. Okay, sometimes the question might say, how far should he row in his boat? How far should he walk on land? In that case, then you would need to find the r, and you would have had to find the 10 minus x. But this time, they're not asking us for that. So we're just going to write out a therefore statement, and let's round this to 4 decimal places. So square root of 12 is approximately 3.4641 kilometers. Okay, so the fisherman should land 3.4641 kilometers along the shore from his current position. And we still haven't done our little verification step, so that is going to be the last thing we have to do. So we want to do a quick little check to make sure it is in fact a minimum time that we found. So either the first or second derivative test here. So we can check, for instance, when x equals 3 and when x equals 4. And we're going to plug that into t prime. So if we plug it in, we would get a minimum, and then we would also get increasing on the other side, which means that our overall point is a min. Okay, so our check did work. Okay. And that is the end of the example.